Hello, everyone, and welcome to week number 5 of Geology 100 lecture. Our topic for this week, as you can see on the screen here, is minerals. Probably one of the more exciting topics that we'll get into this semester, but also one of the preface topics before we can dive deep into rocks and some of the more niche topics. Now, we are at week number 5 of this course, which means the past weeks we have talked about the more major topics of this course, that being the formation of our universe with the formation of our solar system and thus the formation of our Earth. And then we dove deep into Earth's interior and studying the Earth's interior, looking at all the different layers that comprise our Earth, going from Earth's core all the way up towards Earth's surface. We then talked about how Earth's surface is changing and morphing through time, with the biggest driver being plate tectonics. Now we're going to dive deep into minerals. Now, it's important that we study minerals for many different reasons. One is that minerals comprise a lot of the things that we as humans use on the day-to-day basis. But they also reinforce a lot of the topics we've already talked about. When we talked about the differentiation of Earth's interior with the rising and the floating of the lighter elements and the sinking of the more heavier and denser elements. Now, the rising and the sinking of certain elements based on their density then plays into the minerals that thus form and those we see that are exposed on the surface of the Earth, and how are those different from the minerals that may comprise Earth's interior. They also help us glean a little bit more information about plate tectonics. They help us study mass land movements, but also natural disasters. And they're also important for things for economic purposes, looking for different kinds of ores, looking for non-renewable energy resources like oil and gas. If you're in the lab, you'll get a little more hands-on look with some of these minerals. But as for the lecture, we're going to go into detail about what minerals are, how minerals are determined, how we identify them in hand samples, and how we are able to distinguish them in hand samples as well. There are 8 major elements that comprise the majority of our major minerals, silicates, that comprise the rocks that form the surface of our Earth. And those elements are on the screen here: sodium, magnesium, oxygen, aluminum, silicon, iron, potassium, and calcium. Now, there are minerals that contain others of these elements, but more in trace samples and trace amounts. Now, what are elements? Elements are substances that cannot be broken down by chemical means, and they're comprised of atoms. Now, each one of these atoms are denoted and recognized for the number of protons that are within and located within the atomic nuclei. So for example, on the screen, we have the element of carbon. Now, if you're looking at a periodic table of elements, you may see like this, where the number on top of this box here of this letter C is the atomic number. Now, the atomic number are the number of protons in the atom's nucleus. Each element is comprised of a certain amount of protons. So carbon, noted by the elemental symbol C here on the screen, carbon will always have an atomic number of 6, which means that there are 6 protons that reside in that atom's nucleus. And we also have another number on the screen here, and that is the atomic weight. So the number here is 12.011. Now, the atomic weight is the average mass of an atom of a given element. Now, the atomic weight takes into account the mass of the protons, the mass of the neutrons, and the mass of the electrons. Now, if we go back to our basic chemistry, an atom's nucleus is comprised of the protons and the neutrons. And spinning, for the most part, in its basic sense, outside of that atom are the electrons. A majority of the atomic weight comes from the protons and the neutrons, whereas the electrons are really, really low in mass in comparison. Now, why are we talking about elements, and why is it important? Well, the topic for this week is minerals, and minerals are comprised of elements. And as we know, looking at Earth's interior, that there are 8 elements that make up a majority of Earth's crust and mantle, which are those elements that I talked about in the previous slides, which are oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium, where you can see that majority of Earth's crust and mantle is comprised of oxygen and silicon. Now, those will come into play heavily later on in this video and this PowerPoint. These common elements can combine in many different ways, and the ways that they combine determine what kind of mineral will form and the minerals that we are able to recognize. Minerals are distinguished by not only their elemental composition, but some other things as well, which we will get into very shortly. Some minerals are comprised of many elements, whereas there are some minerals that are only comprised of a couple elements, like quartz here on the screen, which is comprised of just silicon and oxygen. Now, there are also some minerals that are comprised of just one element, carbon, for example. Now, diamond and graphite are both comprised of carbon. So why are they different minerals if they both have the same element? Well, minerals are described further than just the elements or the composition of the minerals in the first place. Minerals, and I hope that you all can remember this definition verbatim, minerals are naturally occurring inorganic solid compounds of one or more elements with a limited chemical composition and a definite atomic structure or arrangement. Now, we talked about the composition where a mineral can be comprised of at least one or more elements. But what does it mean to be naturally occurring, inorganic, and having a definite atomic structure or arrangement? Now, those other parts of the definition we will talk about right now. Naturally occurring essentially means that they are created by Earth processes in a natural way. Now, there are some cases where we as humans have engineered some synthetic minerals in a laboratory setting. A mineral is only considered a mineral if it is naturally occurring. If it was created in a lab, it is not considered a mineral. It is considered a synthetic mineral. Inorganic means that it does not necessarily contain carbon. Now, there are some minerals that do have carbon, but it's not the organic form of carbon, which means it's not the organic carbon compound, where carbon is attached to hydrogen atoms to create CH chains. So those organic carbon compounds. So a mineral must be inorganic, which means it does not contain that organic form of carbon. So we do have minerals that have carbon, just carbon, but we also have minerals that have carbon and other elements. But those other elements are not those hydrogen atoms bonded to those carbon atoms to form those organic compounds of carbon. Solid means that the mineral is able to indefinitely maintain its shape and its structure at stable temperatures. So stable temperatures would mean that it is not extremely cold so that it can crack, or it's not extremely hot where it can begin to melt. Now, we talked about minerals being comprised of one or more elements. So minerals are defined by their chemical formulas, which essentially means the elements that comprise it and the ratios in which those elements are comprised. So the elements that make up each one of these minerals are defined. So quartz will always be comprised of silicon and oxygen, as you can see on the screen here. Calcite will always be comprised of calcium, carbon, and oxygen. Halite will always be comprised of sodium and chlorine. And now that brings us to the last part of our definition of a mineral, the orderly arrangement of atoms, or a definite crystalline structure, however you want to say it, is that minerals must have a crystalline structure, which means that each one of those elements, and thus each one of those atoms, is placed in a certain space and shape. So most solid materials in themselves are crystalline. Solids that lack some kind of internal atomic arrangement and orderly arrangement of these atoms are called glasses. So a glass would not be considered a mineral because it does not have an orderly arrangement of atoms. Now, going the basis of the definition of a mineral, we know that there are many elements that we have recognized through time. And if each one of these elements is able to combine with another element or elements, we could probably create a lot of different minerals. And that holds to be true. So how do we identify all of these minerals? Well, we essentially can do it in two main ways. Either through the use of some kind of instrument, like an X-ray diffraction or a scanning electron microscope, or we could do it in hand sample through observable identification properties. If you were in my Geology 100 laboratory, our labs that we have starting in a few weeks will begin to go through mineral identification. Now, mineral identification is definitely a skill, and it requires the complete learning of some of these physical properties and how we can test for them in hand sample. Some of these physical properties are very common and ones that we as geologists continue to use out in the field. Some of these common properties are color, streak, luster, hardness, fracture, cleavage, habit, and specific gravity and heft. You can essentially break these down into what does the mineral actually look like? What's its color? Is it hard or is it soft? Can I scratch something with the mineral? And what happens when that mineral breaks? We'll first start with color. So there are many minerals that have a very characteristic color. We have three images on the screen here, and these are three different kinds of minerals. On the top right, we have wolfenite. Now, wolfenite is described not only by its blade-like habit, essentially how that mineral grows, but also by this very burnt orange color. On the bottom right hand of the screen here, you all may know this mineral. This is pyrite, or fool's gold, as some people call it, because it does look like gold, but it is not gold, it is pyrite. And on the bottom left-hand screen here, we have, well, it's actually two minerals, but we are going to focus on the blue mineral in this image, and that is kyanite. Now, kyanite is identified mainly by its color, but also its habit, so how that mineral grows in the first place. There are some other ones as well. Now, if you're in my Geology 100 lab, you'll see some of these as well. Sulfur, which you've probably heard before, that stinky, rotten egg smelling mineral. It has a neon yellow color. There's also potassium feldspar, which gives a nice pink color. And there's also a amazonite, which gives this nice aqua green color. Now, you have to be careful because there are some minerals that can have many different colors, and sometimes color is not characteristic of a given mineral. A good example would be quartz. Quartz can come in many different colors, and we essentially can give it many different flavors and varieties. So on the screen here are all different types of quartz. So on the bottom left-hand side of the screen, we have just normal clear quartz. On the center here, bottom center, we have rose quartz, so it's a pink quartz. On the bottom right, we have this smoky quartz is what we call it. And on the top right hand here, we have amethyst, which is also a type of quartz. Now, quartz gets its change in color due to impurities. So as the mineral is forming and solidifying, there are some elements that essentially get shoved in between the crystalline structure. The next mineral property we have is streak. So now how I like to think about a streak is if you were to take that mineral and scratch it on a ceramic plate, what's the powder, that residue, what's the color of that powder or residue that's left behind? So on the screen here, this plate is a ceramic plate. And if you take a mineral like hematite and scratch it across that plate, that mineral is essentially going to leave some kind of residue, some kind of material on it. Now, some of these minerals we can identify solely based on their streak. So if you were to scratch hematite onto the ceramic plate, it will leave this reddish brown streak. Color is extremely variable. So thinking back to quartz or wolfenite or sulfur, right? For the most part, streak color is not. Most streak colors tend to be this reddish brown. Sometimes you get black, sometimes you get clear, or sometimes you get a dark green. But for the most part, you don't get the other types of colors like purples, yellows, very bright reds. You don't usually get those. The next type of mineral property we have is luster. Now, luster is how light interacts with the surface of the mineral. And how I like to think about luster is if you were to take a really thin piece of that mineral and hold it up to the light, could you see through that mineral, the light, or would that mineral, that thin section, block out the light? We essentially have two main types of luster, metallic and non-metallic. So if you hold up the thin section to the light, with metallic luster, you wouldn't be able to see through it. With non-metallic, you would be able to see through it. Metallic essentially looks like a metal. So this image that we have on the right-hand side of the screen here is pyrite that has a metallic luster. On the left-hand side of the screen here, we have kaolinite, which is a non-metallic luster. Now, there are many different varieties of non-metallic luster, which we will talk about these in depth in the lab. So hopefully you are also enrolled in the Geology 100 laboratory because you will go through these in depth. Some of these non-metallic lusters are vitreous, so glassy, so you can see through it just like glass, earthy, dull, waxy, silky, pearly, and resinous. The next type of mineral property we have is hardness. And no, it's not how hard the mineral is. It's essentially the mineral's resistance to scratching. So whether or not if you were to take that mineral and scratch it across something, would that object that you scratched with your mineral in question, would that mineral scratch that object? Or would the mineral scratch as a result of that object? Now we are able to test hardness using a relative scale of certain minerals. We call this the Mohs hardness scale, where 1 on the Mohs hardness scale would be considered the softest, so the most readily scratchable mineral, and 10 being the hardest, so the least readily scratchable mineral. Now, the Mohs hardness scale was created as a way to easily identify some minerals out in the field. Now, it was created by Friedrich Mohs in 1812. On the screen here is a graphical example of the Mohs hardness scale. As you can see, it is not a linear scale. So for example, the Mohs number jump from 3 to 4 is about a 25% increase, whereas the Mohs jump from 9 to 10 is about a 300% increase. Each one of these numbers on the Mohs hardness scale was assigned an arbitrary mineral. So on the Mohs hardness scale, mineral number 10, that's assigned for Mohs hardness number 10, which means that it is the hardest, mineral number 10 can scratch number 9, and number 9 can scratch number 8, and 8 can scratch 7. But 6 cannot scratch 7. 7 would scratch 6. So that is important to remember for the Mohs hardness scale. Now the minerals that are assigned for these, I ask that you all try to memorize. So number 1 is talc, 2 is gypsum, 3 is calcite, 4 is fluorite, 5 is apatite, 6 is feldspar, 7 is quartz, 8 is topaz, 9 is corundum, and 10 is diamond. Now, if you were in my Geology 100 laboratory, you are given these minerals that comprise this Mohs hardness scale, except for number 10, that's a diamond. Here's another look at the Mohs hardness scale. Now, as you can also see here, on the left-hand side of this diagram, you can see all the minerals that I described. On the right-hand side of here, you see some common objects. Now, if you don't readily have these minerals out in the field in order to test for mineral hardness, you can essentially bring a kit of some of these common objects, like a streak plate, so that ceramic plate I talked about, a glass plate, so just a piece of glass, a knife blade, a nail, a copper penny, or your fingernail. The next type of mineral property is the habit. So the habit is just the arrangement of each one of the faces of a crystal. So the face of the crystal is each one of these, for the most part, relatively speaking, these flat portions. So there are some minerals that are really well identified by how their crystal grows in the first place and what these crystal faces look like. So for example, crystal quartz makes this nice little prismatic shape, whereas something like pyroxene makes these shoe boxes, or halite makes these nice little cubes. It just depends. The final type of mineral property that we talk about is fracture and cleavage. Now, this is a little bit more of harder to grasp topic, but in its basic sense, how I like to think about it is if you were to take the mineral sample and throw it across a room onto a hard surface, how would that mineral break? Now, minerals tend to break along preferential planes of weaknesses. Now, those planes of weaknesses are defined by the actual overall arrangement of those atoms in the first place. Now, remember, each mineral is defined by its composition and has a definite internal structure. So a definite crystalline structure or a definite atomic structure. So it's essentially how are each one of those atoms aligned preferentially towards one another. Now, if you looked at the PowerPoint before watching this video, you would have learned about the different types of atomic bonds. So we have stronger bonds and we have weaker bonds. There are some minerals that are comprised of both stronger bonds and weak bonds. So the mineral will more likely break along those weak bonds. Whereas there are some minerals that are only comprised for the most part of one type of bond. So it's going to break sometimes in a curvilinear pattern, or just in an area where that bonding structure is at its weakest. The first type of way that a mineral breaks is called fracture. So with fracture, there are no preferential planes of weakness, which means that there are equal bond strengths in all directions. So if you were to throw that mineral across a room, it will always break differently. We have two main types of fracture, and that's irregular fracture and conchoidal fracture. Now, irregular fracture just means that it breaks irregularly. So it just looks all jagged and distorted. So a good example would be garnet here on the right-hand side of the screen. So you can see here, it doesn't have any kind of orderly breakage or orderly fracture. On the left-hand side of the screen here is what we call conchoidal fracture. Now, conchoidal fracture essentially makes these concentric cones. Looks like it fans out. Conchoidal fracture is commonly found in minerals like quartz and olivine. Now, each one of these fractures is determined by the bond strength of the atomic structure of each individual mineral in the first place. The next type of mineral breakage that we have is cleavage. So fracture means that there's no planes of preferential weakness, whereas cleavage is these minerals will break along planes of weakness that are defined by the atomic structure. So in this case, maybe these minerals contain both strong and weak bonds. So the mineral will more likely break along those weak bonds than those stronger bonds, because it's easier to break those bonds that don't necessarily want to hang on to one another, whereas a stronger bond will do everything in its power in order to hang on to one another. Cleavage planes, essentially those surfaces in which those minerals will preferentially break, they can produce these flat and shiny surfaces. So if you're in the lab, that is one way you can identify some of these cleavage planes, essentially where these surfaces of breakage are occurring. Cleavage is described and defined by the number of planes. So how many different directions of breakage are there, essentially those that are perpendicular to one another or oblique to one another, and at which angle they break. Good examples of cleavage I'll talk about here on the screen here. So the first one would be one direction of cleavage, which means that the mineral will break in just one plane of weakness. Now, each one of these planes can break many different times, but each one of these planes are parallel to one another. So it's still technically considered one plane. A good example of a mineral that has one plane of cleavage is mica. So when you break mica, it breaks off into these nice little sheets. Another term for one direction or one plane of cleavage is called basal cleavage. The next one is two directions of cleavage at 90 degrees, which means that there are two planes of cleavage that intersect one another perpendicularly at 90 degrees. So a good example of this would be potassium feldspar. So this pink mineral on the screen here. So we have a plane of cleavage here and a plane of cleavage here. Now the angle where these two planes intersect one another is at 90 degrees, so a right angle. We also have two directions of cleavage that are not at 90 degrees. So a good example is amphibole on the screen here. So you can see that we have one direction of cleavage here, one direction of cleavage here. But unlike the feldspar just above it, the angle at which those two planes intersect is not at 90 degrees. They're at 60 degrees, so at a much more shallower angle. The final directions of cleavage that I'll talk about will be 3 directions at 90 degrees and 3 directions not at 90 degrees. So a good example of this would be halite. So because it has 3 directions at 90 degrees, essentially means it forms these nice little cube structures. So halite or table salt, depending on how you break it, even if you have these tiny microscopic pieces of halite or table salt, if you were to look down a microscope, they would all make these nice little cubes. So as you can see on the screen here, there's one plane here, one plane here, and one plane on the other side here. So think about it as like an X plane, a Y plane, and the Z plane. Then we have 3 directions not at 90 degrees. So a good example of this would be calcite. So as you can see on the screen here, we have one direction of cleavage here, so one plane. We have one plane that's going up and down, and then we have another plane on this side of the mineral. Now we've talked a lot about what minerals are and how we identify them in hand sample. The last thing we need to discuss are how minerals are formed and why do they form in the first place. Now in the PowerPoint, I provided a nice little mineral animation that goes through the definition of the mineral, but also the geologic processes that form minerals in the first place. I have provided another brief video on Canvas that goes into detail about the 3 main processes that form minerals and how minerals are formed. In its basic sense, minerals form from the solidification of some kind of melt. They form from the evaporation out of some kind of fluid, and they can form from biogenic processes. So organisms, mainly marine organisms, have a large effect on how minerals can form in our oceans in the first place. But in order for us to really reinforce the formation of minerals and how they form in the first place, we need to talk about rocks. Rocks are essentially a conglomeration of minerals. Rocks are comprised from at least one or more minerals. So minerals are the building blocks of rocks, whereas elements and atoms are the building blocks of minerals. So what is a rock? A rock is a naturally occurring cohesive aggregate of one or more minerals. So just like I've asked you to remember verbatim the definition of mineral, I also ask that you remember verbatim the definition of a rock. So just like a mineral, rocks are also naturally occurring, which means they're not manufactured. So concrete and brick are not considered rocks because they are not naturally occurring. Those are man-made. The next being coherent means that rocks are held together by some interlocking grains or by a natural cement. The third is an aggregate, which means it is a sum of many minerals. And sometimes a rock is just comprised of one mineral, but has undergone some kind of transformation in order to create and turn it into a rock in the first place. Now the terms coherence and aggregation may be a little confusing right now, but we will go into more detail about these 2 terms when we start diving into the actual rock types, specifically igneous and metamorphic rocks. Rocks are naturally occurring, and they form from a variety of processes. We have rocks that form deep down inside of our earth at depth. We have rocks that form on the surface of our earth. We have rocks that form in the middle of our oceans. Rocks can also change from one form to another. You can take a granitic rock, and turn it into a sedimentary rock. Or you can take a granitic rock, a granite, igneous rock, and turn it into a metamorphic rock. We call this change from one rock to another the rock cycle. And it's called a cycle for a reason, because each rock type can form one another. Here's a basic diagram of the rock cycle, and I'll give you an example of us walking through it really quickly. So let's say we have a magma chamber that forms deep down inside of our earth, right? So a magma, essentially a melt, this fluid is very, very hot. So how do we turn this melt, this magma, into a hardened rock? We need to cool it down. So let's say through time, this magma chamber slowly makes its way towards the surface. It's getting less pressure on top of it, and it's also getting a little bit cooler because it's moving away from Earth's core, which we know is extremely hot. As that magma begins to cool, it can become an igneous rock. Or that magma can breach its way abruptly through the surface in the form of a volcano and breach out and spill over on Earth's surface in the form of lava, and then that lava cools. In either case, you've created an igneous rock. Now let's say that igneous rock is exposed to Earth's surface for many thousands and maybe even millions of years. Earth's natural systems, the surface processes, will take over. So rain will slowly erode that rock away. Or maybe the wind will carry these tiny pieces. Or maybe each one of these pieces will fall in a stream and make its way towards the ocean. As each one of these fragments of this one giant coherent igneous rock start to make their way and get affected by Earth's surface processes, they will eventually turn into what we call sediment, which are just pieces of material that are either of igneous rocks, sedimentary rocks, or metamorphic rocks. Let's say through time we accumulate sediment, and we accumulate more and more sediment. So now we have the weight and the pressure of the sediment, of the younger sediments on top, pushing on the sediments that maybe have accumulated thousands of years or even millions of years prior. We call this a burial of this material, and eventually will compact and they will cement together. So maybe we turn it into a sedimentary rock. And let's say that all of a sudden that sedimentary rock is slowly uplifted towards Earth's surface due to plate tectonics. It then is exposed back to Earth's natural system processes, maybe turns into sediment, and then is buried again. But let's say the sedimentary rock just continues to get buried. It is then exposed to intense heat and pressure. And each one of those rock and mineral grains, those interlocking mineral grains, will slowly change through time because it is in place under intense amount of temperatures and pressures. It will then, what we begin to call, is metamorphose, which means that it undergoes a solid state change from one thing to another. That's essentially the rock cycle in a nutshell, where you can take an igneous rock and expose it to Earth's surface and eventually it turns into a sedimentary rock. And that sedimentary rock, you can bury it deep down and underneath Earth's surface and metamorphose it. Or maybe you had that metamorphic rock that was metamorphosed from a sedimentary rock or igneous rock that was buried and in place under intense amounts of temperatures and pressures. So as you can see, the rock cycle is very confusing and is complicated because you can't necessarily determine or decide what's going to be the fate of one small fragment of a rock. Now, for the remainder of this PowerPoint, you're going to go through the basics of how we identify rocks, through texture, through composition, through what each one of the individual grains, the minerals in those rocks look like. You also go through some basics of how they form and kind of the trajectory of how we as geologists have identified rocks and considered the rock cycle in the first place. Now, don't worry, a lot of these terms may be confusing at first, but we will be going over each and every one of these as we talk about the individual rock types. This intro to the rocks and the rock cycle is just supposed to be the beginning. I just want to expose you all to what rocks are in the first place so that we can solidify, but also reinforce the formation of minerals in the first place.